How's it going? So today, what we're going to be doing is we're going to be doing a bunch of examples of prove or disprove. Okay. So remember, for universal statements, if we want to disprove them, we just need one counterexample, right? And so we're just going to be looking at a couple different problems and being like, trying to figure out some strategies, right? Trying to figure out whether we want to prove them, whether we want to disprove them, and we'll kind of talk about that. So let me share my screen here. And one good thing to try is kind of like there exist proofs is you just try very small examples to see like kind of how the proof would go and everything like this. So let's just try this first one, right? So the first one says, hey, the sum of two odd numbers or integers is even. So we want to figure this out, whether this is true or false, right? And you know, we start with just a simple example. Let's try like 3 plus 5. Well, 3 plus 5, that's 8, and that's even. So we go, okay, it might be true. Let's try a different one. 7 plus 9. This is 16. Okay, that's also even. So we tried a couple examples. We saw they were true. Maybe we're going to try and prove this. So let's try it. So we say, okay, let x and y be odd integers. Okay, so then we write down the definition, right? That's kind of how we always start. We say, okay, we're going to declare our variables, and then we're going to write down our definition. This means that then x equals 2k plus 1, and y equals, I don't know, choose your other favorite letter, 2j plus 1 for some k and j in the integers. Okay, and remember what we're trying to do here, the sum, right? So we're adding them. So now it says x plus y. Well, this is 2k plus 1 plus 2j plus 1, which if we do this, we get 2k plus 2j plus 2, which is the same thing as 2 times k plus j plus 1. Okay, so we have 2 times this other integer, right? And we say k plus j plus 1 is an integer, so x plus y is even. That's going to be kind of our strategy for everything. It's like, okay, we try a couple examples. Oh, are these examples coming out true? Maybe, maybe not, right? If they're not coming out true, boom, we have a counterexample. If they do come out true, then, we try to work with it. And that's generally a good strategy, but it doesn't always work, right? So for example, let's try number 2. So number 2, right, we say for every positive integer n is this expression prime, right? And prime means there's exactly 2 divisors, 1 and itself, right? You'll also notice, right, that 1 is not prime by this definition. So we try it and we'll say, okay, we set n equal to 1, and this gives us 1 squared plus 41 plus 41, which is 83. And you start thinking, okay, is 83 prime? Well, it's not even, so 2 doesn't go into it, right? And neither do any of the other even numbers. And so then you start going, oh, well, does 3 go into it? No. Okay. Does 5? No. Does 7? Right? And you kind of play this game, you go, 83 is prime, so 83 is not going to work. Okay, we try another one. So like n equals 2. And that says 2 squared plus 41 times 2 plus 41. And what's this going to be? This is going to be 4 plus 82 plus 41. So this is going to be 82 plus 45, and it's 127. All right, and we start going as 127 odd. And you go, well, once again, it's not even. So then I start checking all of these numbers, and you get that, hey, actually 127 is prime, right? And you go, dang, okay, so maybe it is true. And then so you start to try and prove it, but you can't get anywhere, right? And the reason why you can't get anywhere is because this is actually false. And the first number that actually works is 41. So n equals 41 is a counterexample. Okay. So it doesn't always work where, you try the small numbers and it fails, but sometimes it's a good strategy. Okay, let's try 3. Okay, 3 we've seen before, but let's just go through it, right? Is this true or false? And I start going, oh, I don't know. If it's gonna be true, it better be true for at least like singleton sets with only one element. So I say, okay, let A be 1 and B equal 2. Okay, so we got 1 and 2, and let's just see what happens, right? So A union B is going to be 1, 2. Okay, so then we start writing out the power set of A. Well, the power set of A is just the empty set and the set containing 1. Okay. And we can already kind of see, right, that the power set of B is going to be the empty set and then the set containing 2, right? Oops. And so we start doing this, and then we find out that, hey, the power set of this union, right, we're never going to get the set 1, 2 in here, right? So if we take P A union PB, we get the empty set, the set containing 1, and the set containing 2, but it does not contain, right, doesn't have 1, 2 as a subset. Okay, so you can kind of start playing these games and you try to figure it out. So I'll let you try 4. Okay, I'll let you try 4, but what I want to do is kind of do 5 together, and then we'll go from there. So number 4, a quick note on number 4. So 4 is actually true, and there are so many possible answers. So there's infinitely possible answers. And number 4 is slightly different, right? Because it says there exists. So you just have to come up with a set, right? Just have to come up with a set. Or what's it say? It says where the real numbers are a subset of it, and 0, or not 0, the empty set is an element of X. So really all you need, right? You need some set with the real numbers and the empty set as a subset. So you can come up with the set. There's one that's kind of nice, right? But any set with this property will actually work. So let's try 5. Let's try 5. And I'm going to do it all the way down here. And so 5 is a little different, right? It says there exists a P and a Q, and they're prime, for which P minus Q is 97. I don't know. You could try all these different primes, right? And try to see if you can get 97, and maybe you can do it, maybe you can't, right? And you're trying these primes, but you're going to need big primes, right? You're going to need a big prime P, and then maybe try to subtract off a small prime Q, or maybe you need 2 massive primes, P and Q, like in the millions, right? And then try to figure it out. But let's just let's see what we can do, right? So I'm looking at this and I go, man, I have no idea. I have no idea. But what if I negate this statement? So let me just see what the negation is. So the negation says, for all P and Q prime, so for all prime numbers P and Q, P minus Q is not equal to 97. That's the negation, right? And so if the original statement was false, then this statement would have to be true, right? And so we could try to rewrite this and say, like, if P and Q are prime, then P minus Q does not equal 97. Okay, now we have an if then. And but I'm looking at this and I'm going, man, I really still have no idea. So what if I tried the contrapositive of this negation? Right? Because this is hard for us. So this says if P minus Q equals 97, then, well, what's that mean? Then P and Q aren't prime. Maybe this is easier for us. Maybe this is easier for us. And it could be. It could be. So let's try it. So let's try. Generally with prime numbers, the best thing to do is contradiction. That's just kind of a general rule. So we'll try it. So we'll assume to the contrary. Okay, that there exists a P and Q that are prime. Where P minus Q equals 97. Okay, we're trying this. Prime numbers are either odd or the number 2. So we need cases. So case 1, right? Case 1 is Q equals 2. So if Q equals 2, what does that mean? Well, that means that P minus 2 equals 97, or this tells you exactly what it is. It says that P equals 99. But note that 99 is equal to 9 times 11, and so not prime. Okay, so this didn't work for us. This didn't work for us because we said we needed both P and Q to be prime. Okay, so we tried the next one. Case 2. What if Q is odd? Okay, so it's not 2, it's some odd number. So by definition, that just means Q equals 2K plus 1. Okay. So now we substitute some stuff in. We get P minus 2K plus 1 equals 97. And I start doing some arithmetic, and this really says that P minus 2K is equal to 98. Okay, I add 2K, so P equals 98 plus 2K. Oh no, this is not going to work for us because this is 2 times 49 plus K. Thus, P is even. P is even. That's not good for us. But that would mean that P is equal to 2. Okay, so P is even. Thus, P equals 2. Because it's an even prime. Remember, P and Q both have to be prime, and the only even prime is 2. So this means that 2 minus Q equals 97. Oh, this isn't going to be good for us. This means that Q equals negative 95. Well, Q is not prime then. So this is our contradiction. Therefore, no such P and Q exists. Okay, so if no such P and Q exists, what did we just show? Well, we just showed the negation was true, right? We showed the negation was true, which means the original statement was false. Okay, so it took kind of a long way to get there, but sometimes showing negations are true, it can be easier, right? So we showed there can't exist something, right? We showed there absolutely can't exist something. So that's kind of like my big remark for this one, right? Is a good way to see if an existence statement is true or false is by negating the statement and seeing what you get. Okay. Okay, that's all I want to do for this video. So we did 1 through 5, really. You just have to give the example for 4. 6, 7, and 8, I want you to go ahead and try those and then let me know if you have any questions. And I will see everyone next time.